Let's return to the company that is faced with the question of whether or not they should demonstrate their new battery. The actual voltage is specified as 2.4 volts. If the demonstration is successful, the purchasing company will commit to purchasing thousands of these batteries per month. And with such a large and expensive purchase, they need to be certain that the specification is met with very low chance of failure. The demonstration will consist of conducting a random selection of 50 batteries. In the previous video we said 200, but let's chop it down to 50, and then test them. The testing process is destructive and therefore expensive. Now, since the sample size is at least 30, we know that the sampling distribution of sample means is approximately normal. Also, since the sample mean is an unbiased estimator for the population mean, the distribution looks like this provided the population mean is mu equal to 2.4 volts. It would have this nice normal shape where at the population mean of 2.4 volts. And remember, this is because what we know from the central limit theorem, as long as n is at least 30, then the distribution of the sample means will be normal. And since the sample mean is an unbiased estimator of the population mean, then this population mean will be right here in the middle. We already know from our study about the normal probability distribution that it would be very unlikely that a random sample would generate a mean that would land in either tail of the distribution if the population mean is, in fact, mu equal to 2.4 volts. Again, from what we know about the normal distribution, if this mean is actually 2.4 volts, and that's what's in question, is this mean actually 2.4 volts? But if it is, it would be very unlikely that a sample mean would be way out here in either tail. And we can specify how far out in these tails that we want. We can make it as unlikely as we want. But that's the whole key, is this unlikely thing. It's just unlikely that we would land way out here if the population mean is 2.4. So, if the sample mean lands in an unlikely area, then we would have a basis for questioning the validity of the assumption that the population mean is actually 2.4 volts. Now, something that is very key here that we have to remember is that it is impossible to prove anything about a population using sample data. We must rely on our knowledge of probability in order to draw conclusions about populations using sample data. So let's think for a moment about how we would use this hypothetical distribution as a means for using samples to draw conclusions about the population. As a general rule of thumb, an event is considered unlikely if the probability of its occurrence is no greater than 0.05. So if we set up our hypothetical distribution so that the total unlikely area represents 5% of the entire distribution, then we can use it as a guide for drawing a conclusion about our hypothetical population mean. So in other words, we talked about minimizing this potential here for rejecting this assumption. So we are using this rule of thumb that says that if an event has a probability of no greater than 0.05, then it is unlikely. It's an unlikely event. Now, it is possible that we would reject this assumption and this assumption actually be true. But we want to minimize that. And that was that type 1 error that we talked about, rejecting a true assumption. Now, this right here we're calling alpha. Alpha is going to be this area out in these tails, but you remember that from your study of the confidence intervals. Now, if we are testing these batteries and the spec is that they have to be 2.4 volts, equal to 2.4 volts, not greater than or less than, but equal to 2.4 volts, then if that voltage exceeds 2.4 or is too far less than 2.4, then we would be in a situation where this battery is unacceptable, and we would reject that the true population mean is 2.4. So now let's suppose that we randomly selected those 50 batteries to test, and the results are as follows. Let's say that we found a sample mean of 2.35 volts, a standard deviation of 0.15 volts, and with a sample size of 50. Since we do not know the population standard deviation and must use the sample standard deviation as an estimate, it is appropriate that we should use the t-distribution for our probability model. Once again, here's what we have. These are the measures that we got from that sample. From our knowledge of the t-distribution, we know that we'll have to know what the number of degrees of freedom are, and that is going to be one less than the sample size when we are testing about a single mean. And so that's going to be 49 degrees of freedom. So we'll look up then a value, a t-value, in a t-table, or using some technology like StatCrunch or the TI-84 calculator, in order to find out, well, what is that cutoff value, that t cutoff value, that gives us an area in the tail of 0.025 with 49 degrees of freedom. So to find the t-value associated with that place on the t-distribution where we would have 0.025 out in the tail with 49 degrees of freedom, we're going to push second variables distribution, and we're going to want to use this inverse t function. So we're going to push 4. Now this area that's referred to here is the cumulative area up to that point. If we have 0.025 out in the tail, then that's actually going to be 0.975. Our number of degrees of freedom is 49. And then we'll hit paste. And if you have a calculator that's earlier than this particular TI-84 emulator, like an earlier TI-84 or a TI-83, then this is the syntax that you will use rather than entering those values in on that previous screen. Once you have that syntax, which will be the area and then the degrees of freedom, click enter, and you'll get the t-value of 2.010 if we round to 3 decimal places. So we find that that value of t, which we're going to call a critical value, a critical t-value is 2.010. Now, since we know that the t-distribution is symmetric, we know that this value, 2.010, or this value minus 2.010, would leave us with 0.025 as an area in the tail outside of this critical value when we have 49 degrees of freedom. So let's do this. Let's calculate what the associated t-value is with these values for x bar, s, and n when we have an assumed population mean of 2.4. So we have this formula that is very much like the calculation for z when we're calculating z-scores associated with sample means. That'll be x bar minus mu over s over the square root of n, and you see that the only difference is that we have an s here, so we're estimating the population standard deviation using the sample standard deviation. So we plug those values in, and what we wind up with is minus 1.768. Now minus 1.768 is actually in this region in here somewhere. So we didn't quite get over to this critical t-value here, where this sample mean value would be unlikely if the population mean is 2.4. So we haven't really found evidence that would cause us to reject this assumption. Let's kind of write out what we would have done. According to these t-values that we have here and what we know about these areas out here in the tail, here's what would have happened. If this t-test value had been less than minus 2.010, or if this t-test value had been greater than positive 2.010, so in other words, had we wound up in either tail, then we would have rejected that the population mean is 2.4 volts. But that didn't happen. So what we might conclude then is that we didn't actually find sufficient evidence that would lead us to reject this hypothesized mean. So let's write that out. Sufficient evidence was not found to lead us to reject the assumption that the mean is 2.4. And that is the population mean we're testing, mu. Now remember that we cannot prove anything using a sample. All we can do is find whether or not something is particularly unlikely. So way out here in this tail or way up here in this tail. But since that didn't happen, then our sample mean, although it's different from 2.4, it's a little less. But given the other measures, this didn't turn out to be unlikely enough to lead us to reject this assumption that the mean is 2.4.